Some varieties of primitive organism living just at the surface and others living just underneath, each taking advantage of conditions created by the other. The world had its first ecosystem. For many years, scientists knew about stromatolites from fossil formations, but in 1961 they got a real surprise with the discovery of a community of living stromatolites at Shark Bay on the remote northwest coast of Australia. This was most unexpected. So unexpected, in fact, that it was some years before scientists realized quite what they had found. Today, however, Shark Bay is a tourist attraction, or at least as much of a tourist attraction as a place hundreds of miles from anywhere much and dozens of miles from anywhere at all can ever be. Boardwalks have been built out into the bay so that visitors can stroll over the water to get a good look at the stromatolites, quietly respiring just beneath the surface. They are lusterless and gray, and look, as I recorded in an earlier book, like very large cowpats. But it is a curiously giddying moment to find yourself staring at living remnants of the Earth, as it was 3.5 billion years ago. As Richard Fortey has put it, this is truly time travel, and if the world were attuned to its real wonders, this site would be as well known as the Pyramids of Giza. Although you'd never guess it, these dull rocks swarm with life, with an estimated, well, obviously estimated, 3 billion individual organisms on every square yard of rock. Sometimes, when you look carefully, you can see tiny strings of bubbles rising to the surface as they give up their oxygen. In 2 billion years, such tiny exertions raised the level of oxygen in the Earth's atmosphere to 20%, preparing the way for the next, more complex chapter in life's history. It has been suggested that the cyanobacteria at Shark Bay are perhaps the most slowly evolving organisms on Earth, and certainly now they are among the rarest. Having prepared the way for more complex life forms, they were then grazed out of existence nearly everywhere by the very organisms whose existence they had made possible. They exist at Shark Bay because the waters are too saline for the creatures that would normally feast on them. One reason life took so long to grow complex was that the world had to wait until the simpler organisms had oxygenated the atmosphere sufficiently. Animals could not summon up the energy to work, as Fortey has put it. It took about 2 billion years, roughly 40% of Earth's history, for oxygen levels to reach more or less modern levels of concentration in the atmosphere. But once the stage was set, and apparently quite suddenly, an entirely new type of cell arose, one containing a nucleus and other little bodies collectively called organelles, from a Greek word meaning little tools. The process is thought to have started when some blundering or adventuresome bacterium either invaded or was captured by some other bacterium, and it turned out that this suited them both. The captive bacterium became, it is thought, a mitochondrion. This mitochondrial invasion, or endosymbiotic event, as biologists like to term it, made complex life possible. In plants, a similar invasion produced chloroplasts, which enable plants to photosynthesize. Mitochondria manipulate oxygen in a way that liberates energy from foodstuffs. Without this niftily facilitating trick, life on Earth today would be nothing more than a sludge of simple microbes. Mitochondria are very tiny. You could pack 1 billion into the space occupied by a grain of sand, but also very hungry. Almost every nutriment you absorb goes to feeding them. We couldn't live for 2 minutes without them. Yet even after 1 billion years, mitochondria behave as if they think things might not work out between us. They maintain their own DNA, RNA, and ribosomes. They reproduce at a different time from their host cells. They look like bacteria, divide like bacteria, and sometimes respond to antibiotics in the way bacteria do. They don't even speak the same genetic language as the cell in which they live. In short, they keep their bags packed. It is like having a stranger in your house, but one who has been there for 1 billion years. The new type of cells are known as eukaryotes, meaning truly nucleated, as contrasted with the old type, which are known as prokaryotes, pre-nucleated. And they seem to have arrived suddenly in the fossil record. The oldest eukaryotes yet known, called Grippania, were discovered in iron sediments in Michigan in 1992. Such fossils have been found just once, and then no more are known for 500 million years. Earth had taken its first step towards becoming a truly interesting planet. Compared with the new eukaryotes, the old prokaryotes were little more than bags of chemicals, to borrow from the British geologist Stephen Drury. Eukaryotes were bigger, eventually as much as 10,000 times bigger than their simpler cousins, and could carry as much as 1,000 times more DNA. Gradually, thanks to these breakthroughs, life became complex and created two types of organism, those that expel oxygen like plants and those that take it in, like you and me. Single-celled eukaryotes were once called protozoa, pre-animals, but that term is increasingly disdained. Today, the common term for them is protists. Compared with the bacteria that had gone before, these new protists were wonders of design and sophistication. The simple amoeba, just one cell big and without any ambitions but to exist, contains 400 million bits of genetic information in its DNA. Enough, as Carl Sagan noted, to fill 80 books of 500 pages. Eventually, the eukaryotes learned an even more singular trick. It took a long time, 1 billion years or so, but it was a good one when they mastered it. They learned to form together into complex, multicellular beings. Thanks to this innovation, big, complicated, visible entities like us were possible. Planet Earth was ready to move on to its next ambitious phase. But before we get too excited about that, it is worth remembering that the world as we are about to see still belongs to the very small. Chapter 20, Small World. It's probably not a good idea to take too personal an interest in your microbes. Louis Pasteur, the great French chemist and bacteriologist, became so preoccupied with his that he took to peering critically at every dish placed before him with a magnifying glass, a habit that presumably did not win him many repeat invitations to dinner. In fact, there is no point in trying to hide from your bacteria, for they are on and around you always, in numbers you can't conceive of. If you are in good health and averagely diligent about hygiene, you will have a herd of about 1 trillion bacteria grazing on your fleshy plains, about 100,000 of them on every square centimeter of skin. They are there to dine off the 10 billion or so flakes of skin you shed every day, plus all the tasty oils and fortifying minerals that seep out from every pore and fissure. You are for them the ultimate buffet, with the convenience of warmth and constant mobility thrown in. By way of thanks, they give you BO. And those are just the bacteria that inhabit your skin. There are trillions more tucked away in your gut and nasal passages, clinging to your hair and eyelashes, swimming over the surface of your eyes, drilling through the enamel of your teeth. Your digestive system alone is host to more than 100 trillion microbes of at least 400 types. Some deal with sugars, some with starches, some attack other bacteria. A surprising number, like the ubiquitous intestinal spirochetes, have no detectable function at all. They just seem to like to be with you. Every human body consists of about 10 quadrillion cells, but is host to about 100 quadrillion bacterial cells. They are, in short, a big part of us. From the bacteria's point of view, of course, we are a rather small part of them. Because we humans are big and clever enough to produce and use antibiotics and disinfectants, it is easy to convince ourselves that we have banished bacteria to the fringes of existence. Don't you believe it? Bacteria may not build cities or have interesting social lives, but they will be here when the sun explodes. This is their planet, and we are on it only because they allow us to be. Bacteria, never forget, got along for billions of years without us. We couldn't survive a day without them. They process our wastes and make them usable again. Without their diligent munching, nothing would rot. They purify our water and keep our soils productive. Bacteria synthesize vitamins in our gut, convert the things we eat into useful sugars and polysaccharides, and go to war on alien microbes that slip down our gullet. We depend totally on bacteria to pluck nitrogen from the air and convert it into useful nucleotides and amino acids for us. It is a prodigious and gratifying feat. As Margulis and Sagan note, to do the same thing industrially as when making fertilizers, manufacturers must heat the source materials to 500 degrees Celsius and squeeze them to 300 times normal pressures. Bacteria do the same thing all the time without fuss, and thank goodness, for no larger organism could survive without the nitrogen they pass on. Above all, microbes continue to provide us with the air we breathe and to keep the atmosphere stable. Microbes, including the modern versions of cyanobacteria, supply the greater part of the planet's breathable oxygen. Algae and other tiny organisms bubbling away in the sea blow out about 150 billion kilograms of the stuff every year. And they are amazingly prolific. The more frantic among them can yield a new generation in less than 10 minutes. Clostridium Perfringens, the disagreeable little organism that causes gangrene, can reproduce in 9 minutes and then begin at once to split again. At such a rate, a single bacterium could theoretically produce more offspring in 2 days than there are protons in the universe. Given an adequate supply of nutrients, a single bacterial cell can generate 280,000 billion individuals in a single day, according to the Belgian biochemist and Nobel laureate Christian de Duve. In the same period, a human cell can just about manage a single division. About once every million divisions, they produce a mutant. Usually this is bad luck for the mutant. For an organism, change is always risky. But just occasionally, the new bacterium is endowed with some accidental advantage, such as the ability to elude or shrug off an attack of antibiotics. With this ability to evolve rapidly goes another even scarier advantage. Bacteria share information. Any bacterium can take pieces of genetic coding from any other. Essentially, as Margulis and Sagan put it, all bacteria swim in a single gene pool. Any adaptive change that occurs in one area of the bacterial universe can spread to any other. It's rather as if a human could go to an insect to get the necessary genetic coding to sprout wings or walk on ceilings. It means that from a genetic point of view, bacteria have become a single superorganism, tiny, dispersed, but invincible. They will live and thrive on almost anything you spill, dribble, or shake loose. Just give them a little moisture, as when you run a damp cloth over a counter, and they will bloom as if created from nothing. They will eat wood, the glue and wallpaper, the metals in hardened paint. Scientists in Australia found microbes known as Theobacillus concretivorans, which lived in, indeed could not live without, concentrations of sulfuric acid, strong enough to dissolve metal. A species called Micrococcus radiophilus was found living happily in the waste tanks of nuclear reactors, gorging itself on plutonium and whatever else was there. Some bacteria break down chemical materials from which, as far as we can tell, they gain no benefit at all. They have been found living in boiling mud pots and lakes of caustic soda, deep inside rocks, at the bottom of the sea, in hidden pools of icy water in the McMurdo dry valleys of Antarctica, and 11 kilometers down in the Pacific Ocean, where pressures are more than 1,000 times greater than at the surface, or equivalent to being squashed beneath 50 jumbo jets. Some of them seem to be practically indestructible. Deinococcus radiodurans is, according to The Economist, almost immune to radioactivity. Blast its DNA with radiation and the pieces immediately reform, like the scuttling limbs of an undead creature from a horror movie. Perhaps the most extraordinary survival yet found was that of a Streptococcus bacterium that was recovered from the sealed lens of a camera that had stood on the moon for 2 years. In short, there are few environments in which bacteria aren't prepared to live. They are finding now that when they push probes into ocean vents so hot that the probes actually start to melt, there are bacteria even there, Victoria Bennett told me. In the 1920s, 2 scientists at the University of Chicago, Edson Baston and Frank Greer, announced that they had isolated from oil wells strains of bacteria that had been living at depths of 600 meters. The notion was dismissed as fundamentally preposterous. There was nothing to live on at 600 meters. And for 50 years, it was assumed that their samples had been contaminated with surface microbes. We now know that there are a lot of microbes living deep within the earth, many of which have nothing at all to do with a conventionally organic world. They eat rocks, or rather the stuff that's in rocks, iron, sulfur, manganese, and so on. And they breathe odd things, too, iron, chromium, cobalt, even uranium. Such processes may be instrumental in concentrating gold, copper, and other precious metals, and possibly deposits of oil and natural gas. It has even been suggested that their tireless nibblings created the Earth's crust. Some scientists now think that there could be as much as 100 trillion tons of bacteria living beneath our feet in what are known as subsurface lithoautotrophic microbial ecosystems, SLIME for short. Thomas Gold of Cornell University has estimated that if you took all the bacteria out of the Earth's interior and dumped them on the surface, they would cover the planet to a depth of 15 meters, the height of a 4-story building. If the estimates are correct, there could be more life under the Earth than on top of it. At depth, microbes shrink in size and become extremely sluggish. The liveliest of them may divide no more than once a century, some no more than perhaps once in 500 years. As The Economist has put it, the key to long life, it seems, is not to do too much. When things are really tough, bacteria are prepared to shut down all systems and wait for better times. In 1997, scientists successfully activated some anthrax spores that had lain dormant for 80 years in a museum display in Trondheim, Norway. Other microorganisms have leaped back to life after being released from a 118-year-old can of meat and a 166-year-old bottle of beer. In 1996, scientists at the Russian Academy of Science claimed to have revived bacteria frozen in Siberian permafrost for 3 million years. But the record claim for durability so far is one made by Russell Vreeland and colleagues at Westchester University in Pennsylvania in 2000, when they announced that they had resuscitated 250-million-year-old bacteria called Bacillus Perfringens that had been trapped in salt deposits 600 meters underground in Carlsbad, New Mexico. If so, this microbe is older than the continents. The report met with some understandable dubiousness. Many biochemists maintain that over such a span, the microbe's components would have become uselessly degraded unless the bacterium roused itself from time to time. However, if the bacterium did stir occasionally, there was no plausible internal source of energy that could have lasted so long. The more doubtful scientists suggested that the sample might have been contaminated, if not during its retrieval, then perhaps while still buried. In 2001, a team from Tel Aviv University argued that Bacillus Perfringens was almost identical to a strain of modern bacteria, Bacillus maris mortui, found in the Dead Sea. Only 2 of its genetic sequences differed, and then only slightly. Are we to believe the Israeli researchers wrote that in 250 million years, Bacillus permians has accumulated the same amount of genetic differences that could be achieved in just 3 to 7 days in the laboratory? In reply, Vreeland suggested that bacteria evolve faster in the lab than they do in the wild. Maybe. It is a remarkable fact that well into the space age, most school textbooks divided the world of the living into just 2 categories, plant and animal. Microorganisms hardly featured. Amoebas and similar single-celled organisms were treated as proto-animals and algae as proto-plants. Bacteria were usually lumped in with plants too, even though everyone knew they didn't belong there. As far back as the late 19th century, the German naturalist Ernst Haeckel had suggested that bacteria deserved to be placed in a separate kingdom, which he called Monera. But the idea didn't begin to catch on among biologists until the 1960s, and then only among some of them. I note that my trusty American Heritage Desk Dictionary from 1969 doesn't recognize the term. Many organisms in the visible world were also poorly served by the traditional division. Fungi, the group that includes mushrooms, molds, mildews, yeasts, and puffballs, were nearly always treated as botanical objects, though in fact almost nothing about them, how they reproduce and respire, how they build themselves, matches anything in the plant world. Structurally, they have more in common with animals, in that they build their cells from chitin, material that gives them their distinctive texture. The same substance is used to make the shells of insects and the claws of mammals, though it isn't nearly so tasty in a stag beetle as in a portobello mushroom. Above all, unlike all plants, fungi don't photosynthesize, so they have no chlorophyll and thus are not green. Instead, they grow directly on their food source, which can be almost anything. Fungi will eat the sulfur off a concrete wall or the decaying matter between your toes. 2 things no plant will do. Almost the only plant-like quality they have is that they root. Even less comfortably susceptible to categorization was the peculiar group of organisms formerly called Myxomycetes, but more commonly known as slime molds. The name, no doubt, has much to do with their obscurity. An appellation that sounded a little more dynamic, ambulant self-activating protoplasm, say, and less like the stuff you find when you reach deep into a clogged drain, would almost certainly have earned these extraordinary entities a more immediate share of the attention they deserve. For slime molds are, make no mistake, among the most interesting organisms in nature. When times are good, they exist as one-celled individuals, much like amoebas. But when conditions grow tough, they crawl to a central gathering place and become, almost miraculously, a slug. The slug is not a thing of beauty, and it doesn't go terribly far, usually just from the bottom of a pile of leaf litter to the top, where it is in a slightly more exposed position. But for millions of years, this may well have been the niftiest trick in the universe. And it doesn't stop there. Having hauled itself up to a more favorable locale, the slime mold transforms itself yet again, taking on the form of a plant. By some curious, orderly process, the cells reconfigure, like the members of a tiny marching band, to make a stalk, atop of which forms a bulb known as a fruiting body. Inside the fruiting body are millions of spores, which at the appropriate moment are released to the wind to blow away to become single-celled organisms that can start the process again. For years, slime molds were claimed as protozoa by zoologists and as fungi by mycologists, though most people could see they didn't really belong anywhere. When genetic testing arrived, people in lab coats were surprised to find that slime molds were so distinctive and peculiar that they weren't directly related to anything else in nature, and sometimes not even to each other. In 1969, in an attempt to bring some order to the growing inadequacies of classification, an ecologist from Cornell named R.H. Whitaker unveiled in the journal Science a proposal to divide life into 5 principal branches, kingdoms as they are known, called Animalia, Plantae, Fungi, Protista, and Monera. Protista was a modification of an earlier term, Protoctista, which had been suggested a century earlier by a Scottish biologist named John Hogg, and was meant to describe any organisms that were neither plant nor animal. Though Whittaker's new scheme was a great improvement, Protista remained ill-defined. Some taxonomists reserved the term for large unicellular organisms, the Eukaryotes, but others treated it as a kind of odd sock drawer of biology, putting into it anything that didn't fit anywhere else. It included, depending on which text you consulted, slime molds, amoebas, even seaweed, among much else. By one calculation, it contained as many as 200,000 different species of organism, all told. That's a lot of odd socks. Ironically, just as Whittaker's five-kingdom classification was beginning to find its way into textbooks, an unassuming academic at the University of Illinois was groping his way towards a discovery that would challenge everything. His name was Carl Woes, and since the mid-1960s, or about as early as it was possible to do so, he had been quietly studying genetic sequences in bacteria. In the early days, this was an exceedingly painstaking process. Work on a single bacterium could easily consume a year. At that time, according to Woes, only about 500 species of bacteria were known, which is fewer than the number of species you have in your mouth. Today, the number is about 10 times that, though that is still far short of the 26,900 species of algae, 70,000 of fungi, and 30,800 of amoebas and related organisms whose biographies fill the annals of biology. It isn't simple indifference that keeps the total low. Bacteria can be exasperatingly difficult to isolate and study. Only about 1% will grow in culture. Considering how wildly adaptable they are in nature, it is an odd fact. The one place they seem not to wish to live is a petri dish. Plop them on a bed of agar and pamper them as you will, and most will just lie there, declining every inducement to bloom. Any bacterium that thrives in a lab is by definition exceptional, and yet these were, almost exclusively, the organisms studied by microbiologists. It was, said Woes, like learning about animals from visiting zoos. Genes, however, allowed Woes to approach microorganisms from another angle. As he worked, Woes realized that there were more fundamental divisions in the microbial world than anyone suspected. A lot of little organisms that looked like bacteria and behaved like bacteria were actually something else altogether, something that had branched off from bacteria a long time ago. Woes called these organisms archaebacteria, later shortened to archaea. It has to be said that the attributes that distinguish archaea from bacteria are not the sort that would quicken the pulse of any but a biologist. There are mostly differences in their lipids, and an absence of something called peptidoglycan. But in practice, they make a world of difference. Archaea are more different from bacteria than you and I are from a crab or spider. Single-handedly, Woes had discovered an unsuspected division of life, so fundamental that it stood above the level of kingdom at the apogee of the universal tree of life, as it is rather reverentially known. In 1976, he startled the world, or at least the little bit of it that was paying attention, by redrawing. Get straight to work before the victim's defense mechanisms can figure out what's hit them. That is why so many grade A diseases, malaria, yellow fever, dengue fever, encephalitis, and 100 or so other less celebrated but often rapacious maladies, begin with a mosquito bite. It is a fortunate fluke for us that HIV, the AIDS agent, isn't among them, at least not yet. Any HIV the mosquito sucks up on its travels is dissolved by the mosquito's own metabolism. When the day comes that the virus mutates its way around this, we may be in real trouble. It is a mistake, however, to consider the matter too carefully from the position of logic, because microorganisms clearly are not calculating entities. They don't care what they do to you any more than you care what distress you cause when you slaughter them by the millions with a soapy shower or a swipe of deodorant. The only time your continuing well-being is of consequence to a pathogen is when it kills you too well. If they eliminate you before they can move on, then they may well die out themselves. History, Jared Diamond notes, is full of diseases that once caused terrifying epidemics and then disappeared as mysteriously as they had come. He cites the robust but mercifully transient English sweating sickness, which raged from 1485 to 1552, killing tens of thousands as it went, before burning itself out. Too much efficiency is not a good thing for any infectious organism. A great deal of sickness arises not because of what the organism has done to you, but because of what your body is trying to do to the organism. In its quest to rid the body of pathogens, the immune system sometimes destroys cells or damages critical tissues. So, often when you are unwell, what you are feeling is not the pathogens, but your own immune responses. Anyway, getting sick is a sensible response to infection. Sick people retire to their beds, and thus are less of a threat to the wider community. Because there are so many things out there with the potential to hurt you, your body holds lots of different varieties of defensive white blood cells, some 10 million types in all, each designed to identify and destroy a particular sort of invader. It would be impossibly inefficient to maintain 10 million separate standing armies, so each variety of white blood cell keeps only a few scouts on active duty. When an infectious agent, what's known as an antigen, invades, relevant scouts identify the attacker and put out a call for reinforcements of the right type. While your body is manufacturing these forces, you are likely to feel wretched. The onset of recovery begins when the troops finally swing into action. White cells are merciless and will hunt down and kill every last pathogen they can find. To avoid extinction, attackers have evolved two elemental strategies. Either they strike quickly and move on to a new host, as with common infectious diseases like flu, or they disguise themselves so that the white cells fail to spot them, as with HIV, the virus responsible for AIDS, which can sit harmlessly and unnoticed in the nuclei of cells for years before springing into action. One of the odder aspects of infection is that microbes that normally do no harm at all sometimes get into the wrong parts of the body and go kind of crazy, in the words of Dr. Brian Marsh, an infectious diseases specialist at Dartmouth Hitchcock Medical Center in Lebanon, New Hampshire. It happens all the time with car accidents when people suffer internal injuries. Microbes that are normally benign in the gut get into other parts of the body, the bloodstream for instance, and cause terrible havoc. The scariest, most out-of-control bacterial disorder of the moment is a disease called Necrotizing Fasciitis, in which bacteria essentially eat the victim from the inside out, devouring internal tissue and leaving behind a pulpy, noxious residue. Patients often come in with comparatively mild complaints, a skin rash and fever typically, but then dramatically deteriorate. When they are opened up, it is often found that they are simply being consumed. The only treatment is what is known as radical excisional surgery, cutting out every bit of infected area. 70% of victims die. Many of the rest are left terribly disfigured. The source of the infection is a mundane family of bacteria called Group A Streptococcus, which normally do no more than cause strep throat. Very occasionally, for reasons unknown, some of these bacteria get through the lining of the throat and into the body proper, where they wreak the most devastating havoc. They are completely resistant to antibiotics. About 1,000 cases a year occur in the United States, and no one can say that it won't get worse. Precisely the same thing happens with meningitis. At least 10% of young adults, and perhaps 30% of teenagers, carry the deadly meningococcal bacterium. But it lives quite harmlessly in the throat. Just occasionally, in about one young person in 100,000, it gets into the bloodstream and makes them very ill indeed. In the worst cases, death can come in 12 hours. That's shockingly quick. You can have a person who's in perfect health at breakfast and dead by evening, says Marsh. We would have much more success with bacteria if we weren't so profligate with our best weapon against them, antibiotics. Remarkably, by one estimate, some 70% of the antibiotics used in the developed world are given to farm animals, often routinely in stock feed, simply to promote growth or as a precaution against infection. Such applications give bacteria every opportunity to evolve a resistance to them. It is an opportunity that they have enthusiastically seized. In 1952, penicillin was fully effective against all strains of Staphylococcus bacteria to such an extent that by the early 1960s, the U.S. Surgeon General, William Stewart, felt confident enough to declare, "The time has come to close the book on infectious diseases. We have basically wiped out infection in the United States." Even as he spoke, however, some 90% of those strains were in the process of developing immunity to penicillin. Soon, one of these new strains, called methicillin-resistant Staphylococcus aureus, began to show up in hospitals. Only one type of antibiotic, vancomycin, remained effective against it. But in 1997, a hospital in Tokyo reported the appearance of a strain that could resist even that. Within months, it had spread to 6 other Japanese hospitals. All over, the microbes are beginning to win the war again. In U.S. hospitals alone, some 14,000 people a year die from infections they pick up there. As James Surowiecki noted in a New Yorker article, given a choice between developing antibiotics that people will take every day for 2 weeks and antidepressants that people will take every day forever, drug companies, not surprisingly, opt for the latter. Although a few antibiotics have been toughened up a bit, the pharmaceutical industry hasn't given us an entirely new antibiotic since the 1970s. Our carelessness is all the more alarming since the discovery that many other ailments may be bacterial in origin. The process of discovery began in 1983 when Barry Marshall, a doctor in Perth, Western Australia, found that many stomach cancers and most stomach ulcers are caused by a bacterium called Helicobacter pylori. Even though his findings were easily tested, the notion was so radical that more than a decade would pass before they were generally accepted. America's National Institutes of Health, for instance, didn't officially endorse the idea until 1994. Hundreds, even thousands of people must have died from ulcers who wouldn't have, Marshall told a reporter from Forbes in 1999. Since then, further research has shown that there is or may well be a bacterial component in all kinds of other disorders: heart disease, asthma, arthritis, multiple sclerosis, several types of mental disorders, many cancers. Even it has been suggested in science, no less, obesity. The day may not be far off when we desperately require an effective antibiotic and haven't got one to call on. It may come as a slight comfort to know that bacteria can themselves get sick. They are sometimes infected by bacteriophages, or simply phages, a type of virus. A virus is a strange and unlovely entity, a piece of nucleic acid surrounded by bad news, in the memorable phrase of the Nobel laureate Peter Medawar. Smaller and simpler than bacteria, viruses aren't themselves alive. In isolation, they are inert and harmless, but introduce them into a suitable host, and they burst into busyness, into life. About 5,000 types of virus are known, and between them they afflict us with many hundreds of diseases, ranging from the flu and common cold to those that are most invidious to human well-being: smallpox, rabies, yellow fever, Ebola, polio, and AIDS. Viruses prosper by hijacking the genetic material of a living cell and using it to produce more virus. They reproduce in a fanatical manner, then burst out in search of more cells to invade. Not being living organisms themselves, they can afford to be very simple. Many, including HIV, have 10 genes or fewer, whereas even the simplest bacteria require several thousand. They are also very tiny, much too small to be seen with a conventional microscope. It wasn't until 1943 and the invention of the electron microscope that science got its first look at them. But they can do immense damage. Smallpox in the 20th century alone killed an estimated 300 million people. They also have an unnerving capacity to burst upon the world in some new and startling form, and then to vanish again as quickly as they came. In 1916, in one such case, people in Europe and America began to come down with a strange sleeping sickness, which became known as encephalitis lethargica. Victims would go to sleep and not wake up. They could be roused without great difficulty to take food or go to the lavatory, and would answer questions sensibly. They knew who and where they were, though their manner was always apathetic. However, the moment they were permitted to rest, they would at once sink back into deepest slumber and remain in that state for as long as they were left. Some went on in this manner for months before dying. A very few survived and regained consciousness, but not their former liveliness. They existed in a state of profound apathy, like extinct volcanoes, in the words of one doctor. In 10 years, the disease killed some 5 million people and then quietly went away. It didn't get much lasting attention because in the meantime, an even worse epidemic, indeed the worst in history, swept across the world. It is sometimes called the Great Swine Flu Epidemic, and sometimes the Great Spanish Flu Epidemic, but in either case, it was ferocious. The First World War killed 21 million people in 4 years. Swine flu did the same in its first 4 months. Almost 80% of American casualties in the First World War came not from enemy fire, but from flu. In some units, the mortality rate was as high as 80%. Swine flu arose as a normal, non-lethal flu in the spring of 1918. But somehow, over the following months, no one knows how or where, it mutated into something more severe. A fifth of victims suffered only mild symptoms, but the rest became gravely ill, and many died. Some succumbed within hours, others held on for a few days. In the United States, the first deaths were recorded among sailors in Boston in late August 1918, but the epidemic quickly spread to all parts of the country. Schools closed, public entertainments were shut down, people everywhere wore masks. It did little good. Between autumn of 1918 and spring of the following year, 548,452 people died of the flu in America. The toll in Britain was 220,000, with similar numbers in France and Germany. No one knows the global toll, as records in the Third World were often poor. But it was not less than 20 million, and probably more like 50 million. Some estimates have put the global total as high as 100 million. In an attempt to devise a vaccine, medical authorities conducted experiments on volunteers at a military prison on Deer Island in Boston Harbor. The prisoners were promised pardons if they survived a battery of tests. These tests were rigorous, to say the least. First, the subjects were injected with infected lung tissue taken from the dead, and then sprayed in the eyes, nose, and mouth with infectious aerosols. If they still failed to succumb, they had their throats swabbed with discharges taken straight from the sick and dying. If all else failed, they were required to sit open-mouthed while a gravely ill victim was sat up slightly and made to cough into their faces. Out of, somewhat amazingly, 300 men who volunteered, the doctors chose 62 for the tests. None contracted the flu. Not one. The only person who did grow ill was the ward doctor, who swiftly died. The probable explanation for this is that the epidemic had passed through the prison a few weeks earlier, and the volunteers, all of whom had survived that visitation, had a natural immunity. Much about the 1918 flu epidemic is understood poorly, or not at all. One mystery is how it erupted suddenly all over, in places separated by oceans, mountain ranges, and other earthly impediments. A virus can survive for no more than a few hours outside a host body. So how could it appear in Madrid, Bombay, and Philadelphia all in the same week? The probable answer is that it was incubated and spread by people who had only slight symptoms or none at all. Even in normal outbreaks, about 10% of people in any given population have the flu but are unaware of it because they experience no ill effects. And because they remain in circulation, they tend to be the great spreaders of the disease. That would account for the 1918 outbreak's widespread distribution, but it still doesn't explain how it managed to lie low for several months before erupting so explosively at more or less the same time all over. Even more mysterious is that it was most devastating to people in the prime of life. Flu normally is hardest on infants and the elderly, but in the 1918 outbreak, deaths were overwhelmingly among people in their 20s and 30s. Older people may have benefited from resistance gained from an earlier exposure to the same strain, but why the very young were similarly spared is unknown. The greatest mystery of all is why the 1918 flu was so ferociously deadly when most flus are not. We still have no idea. From time to time, certain strains of virus return. A disagreeable Russian virus known as H1N1 caused severe outbreaks over wide areas in 1933, then again in the 1950s, and yet again in the 1970s. Where it went in the meantime, each time, is uncertain. One suggestion is that viruses hide out unnoticed in populations of wild animals before trying their hand at a new generation of humans. No one can rule out the possibility that the great swine flu epidemic might once again rear its head. And if it doesn't, others well might. New and frightening viruses crop up all the time. Ebola, Lassa, and Marburg fevers have all tended to flare up and die down again, but no one can say that they aren't quietly mutating away somewhere, or simply awaiting the right opportunity to burst forth in a catastrophic manner. It is now apparent that AIDS has been among us much longer than anyone originally suspected. Researchers at the Manchester Royal Infirmary discovered that a sailor who had died of mysterious untreatable causes in 1959 in fact had AIDS. Yet for whatever reasons, the disease remained generally quiescent for another 20 years. The miracle is that other such diseases haven't gone rampant. Lassa fever, which wasn't first detected until 1969 in West Africa, is extremely virulent and little understood. In 1969, a doctor at a Yale University lab in New Haven, Connecticut, who was studying Lassa fever, came down with it. He survived, but more alarmingly, a technician in a nearby lab with no direct exposure also contracted the disease and died. Happily, the outbreak stopped there, but we can't count on always being so fortunate. Our lifestyles invite epidemics. Air travel makes it possible to spread infectious agents across the planet with amazing ease. An Ebola virus could begin the day in, say, Benin and finish it in New York or Hamburg or Nairobi, or all three. It means also that medical authorities increasingly need to be acquainted with pretty much every malady that exists everywhere. But of course they are not. In 1990, a Nigerian living in Chicago was exposed to Lassa fever on a visit to his homeland, but didn't develop symptoms until he had returned to the United States. He died in a Chicago hospital without diagnosis and without anyone taking any special precautions in treating him, unaware that he had one of the most lethal and infectious diseases on the planet. Miraculously, no one else was infected. We may not be so lucky next time. And on that sobering note, it's time to return to the world of the visibly living. Visibly living. Visibly living. Visibly living. Visibly living. Visibly living. Chapter 21. Life Goes On. It isn't easy to become a fossil. The fate of nearly all living organisms, over 99.9% of them, is to compost down to nothingness. When your spark is gone, Every molecule you own will be nibbled off you or sluiced away to be put to use in some other system. That's just the way it is. Even if you make it into the small pool of organisms, the less than 0.1% that don't get devoured, the chances of being fossilized are very small. In order to become a fossil, several things must happen. First, you must die in the right place. Only about 15% of rocks can preserve fossils, so it's no good keeling over on a future site of granite. In practical terms, the deceased must become buried in sediment where it can leave an impression, like a leaf in wet mud, or decompose without exposure to oxygen, permitting the molecules in its bones and hard parts, and very occasionally softer parts, to be replaced by dissolved minerals, creating a petrified copy of the original. Then, as the sediments in which the fossil lies are carelessly pressed and folded and pushed about by Earth's processes, the fossil must somehow maintain an identifiable shape. Finally, but above all, after tens of millions or perhaps hundreds of millions of years hidden away, it must be found and recognized as something worth keeping. Only about 1 bone in a billion, it is thought, ever becomes fossilized. If that is so, it means that the complete fossil legacy of all the Americans alive today, that's 270 million people with 206 bones each, will only be about 50 bones, 1/4 of a complete skeleton. That's not to say, of course, that any of these bones will ever actually be found. Bearing in mind that they can be buried anywhere within an area of slightly over 9.3 million square kilometers, little of which will ever be turned over, much less examined, it would be something of a miracle if they were. Fossils are in every sense vanishingly rare. Most of what has lived on Earth has left behind no record at all. It has been estimated that less than 1 species in 10,000 has made it into the fossil record. That in itself is a stunningly infinitesimal proportion. However, if you accept the common estimate that the Earth has produced 30 billion species of creature in its time, and Richard Leakey and Roger Lewin's statement in the 6th extinction that there are 250,000 species of creature in the fossil record, that reduces the proportion to just 1 in 120,000. Either way, what we possess is the merest sampling of all the life that the Earth has spawned. Moreover, the record we do have is hopelessly skewed. Most land animals, of course, don't die in sediments. They drop in the open and are eaten or left to rot or weather down to nothing. The fossil record, consequently, is almost absurdly biased in favor of marine creatures. About 95% of all the fossils we possess are of animals that once lived underwater, mostly in shallow seas. I mention all this to explain why, on a grey day in February, I went to the Natural History Museum in London to meet a cheerful, vaguely rumpled, very likable paleontologist named Richard Fortey. Fortey knows an awful lot about an awful lot. He is the author of a wry, splendid book called Life, an Unauthorized Biography, which covers the whole pageant of animate creation. But his first love is a type of marine creature called trilobites, which once teemed in Ordovician seas, but haven't existed for a long time except in fossilized form. All trilobites shared a basic body plan of 3 parts, or lobes: head, tail, thorax, from which comes the name. Fortey found his first when he was a boy, clambering over rocks at St. David's Bay in Wales. He was hooked for life. He took me to a gallery of tall metal cupboards. Each cupboard was filled with shallow drawers, and each drawer was filled with stony trilobites, 20,000 specimens in all. It seems like a big number, he agreed, but you have to remember that millions upon millions of trilobites lived for millions upon millions of years in ancient seas. So 20,000 isn't a huge number. And most of these are only partial specimens. Finding a complete trilobite fossil is still a big moment for a paleontologist. Trilobites first appeared, fully formed, seemingly from nowhere, about 540 million years ago, near the start of the great outburst of complex life, popularly known as the Cambrian explosion, and then vanished, along with a great deal else, in the great and still mysterious Permian extinction 300,000 or so centuries later. As with all extinct creatures, there is a natural temptation to regard them as failures. But in fact, they were among the most successful animals ever to live. They reigned for 300 million years, twice the span of dinosaurs, which were themselves among history's great survivors. Humans, 40 points out, have survived so far for 0.5% as long. With so much time at their disposal, the trilobites proliferated prodigiously. Most remained small, about the size of modern beetles, but some grew to be as big as platters. Altogether, they formed at least 5,000 genera and 60,000 species, though more turn up all the time. Forty had recently been at a conference in South America where he was approached by an academic from a small provincial university in Argentina. She had a box that was full of interesting things, trilobites that had never been seen before in South America, or indeed anywhere, and a great deal else. She had no research facilities to study them, and no funds to look for more. Huge parts of the world are still unexplored. In terms of trilobites? No. In terms of everything. Throughout the 19th century, trilobites were almost the only known forms of early complex life, and for that reason were assiduously collected and studied. The big mystery about them was their sudden appearance. Even now, as Forty says, it can be startling to go to the right formation of rocks and to work your way upwards through the eons, finding no visible life at all. And then suddenly a whole Prophalotaspis or Elenellus, as big as a crab, will pop into your waiting hands. These were creatures with limbs, gills, nervous systems, probing antennae, a brain of sorts, in Forty's words, and the strangest eyes ever seen. Made of calcite rods, the same stuff that forms limestone, they constituted the earliest visual systems known. More than this, the earliest trilobites didn't consist of just one venturesome species, but dozens, and didn't appear in one or two locations, but all over. Many thinking people in the 19th century saw this as proof of God's handiwork and refutation of Darwin's evolutionary ideals. If evolution proceeded slowly, they asked, then how did he account for this sudden appearance of complex, fully formed creatures? The fact is, he couldn't. And so matter seemed destined to remain forever, until one day in 1909, 3 months shy of the 50th anniversary of the publication of Darwin's On the Origin of Species, when a paleontologist named Charles Doolittle Walcott made an extraordinary find in the Canadian Rockies. Walcott was born in 1850 and grew up near Utica, New York, in a family of modest means, which became more modest still with the sudden death of his father when Charles was an infant. As a boy, Walcott discovered that he had a knack for finding fossils, particularly trilobites, and built up a collection of sufficient distinction that it was bought by Louis Agassiz for his museum at Harvard for a small fortune, about 45,000 pounds in today's money. Although he had barely a high school education and was self-taught in the sciences, Walcott became a leading authority on trilobites and was the first person to establish that they were arthropods, the group that includes modern insects and crustaceans. In 1879, Walcott took a job as a field researcher with a newly formed United States Geological Survey and served with such distinction that within 15 years he had risen to be its head. In 1907, he was appointed secretary of the Smithsonian Institution, where he remained until his death in 1927. Despite his administrative obligations, he continued to do field work and to write prolifically. His books fill a library shelf, according to Forty. Not incidentally, he was also a founding director of the National Advisory Committee for Aeronautics, which eventually became the National Aeronautics and Space Agency, or NASA, and thus can rightly be considered the grandfather of the space age. But what he is remembered for now is an astute but lucky find in British Columbia, high above the little town of Field, in the late summer of 1909. The customary version of the story is that Walcott, accompanied by his wife, was riding on a mountain trail when his wife's horse slipped on loose stones. Dismounting to assist her, Walcott discovered that the horse had turned a slab of shale that contained fossil crustaceans of an especially ancient and unusual type. Snow was falling, winter comes early to the Canadian Rockies, so they didn't linger. But the next year, at the first opportunity, Walcott returned to the spot. Tracing the presumed route of the rock slide, he climbed 750 feet to near the mountain's summit. There, 8,000 feet above sea level, he found a shale outcrop about the length of a city block, containing an unrivaled array of fossils, from soon after the moment when complex life burst forth in dazzling profusion, the famous Cambrian explosion. Walcott had found, in effect, the holy grail of paleontology. The outcrop became known as the Burgess Shale from the name of the ridge on which it was found, and for a long time it provided our sole vista upon the inception of modern life in all its fullness, as the late Stephen Jay Gould recorded in his popular book Wonderful Life. Gould, ever scrupulous, discovered from reading Walcott's diaries that the story of the Burgess Shale's discovery appears to have been somewhat embroidered. Walcott makes no mention of a slipping horse or falling snow, but there is no disputing that it was an extraordinary find. It is almost impossible for us, whose time on Earth is limited to a breezy few decades, to appreciate how remote in time from us the Cambrian outburst was. If you could fly backwards into the past at the rate of 1 year per second, it would take you about half an hour to reach the time of Christ, and a little over 3 weeks to get back to the beginnings of human life. But it would take you 20 years to reach the dawn of the Cambrian period. It was, in other words, an extremely long time ago, and the world was a very different place. For one thing, 500 million years ago and more, when the Burgess Shale was formed, it wasn't at the top of a mountain, but at the foot of one. Specifically, it was in a shallow ocean basin at the bottom of a steep cliff. The seas of that time teemed with life, but normally the animals left no record because they were soft-bodied and decayed upon dying. At Burgess, however, the cliff collapsed, and the creatures below, entombed in a mudslide, were pressed like flowers in a book, their features preserved in wondrous detail. In annual summer trips from 1910 to 1925, by which time he was 75 years old, Walcott excavated tens of thousands of specimens. Gould says 80,000. The normally unimpeachable fact-checkers of National Geographic say 60,000, which he brought back to Washington for further study. In both sheer numbers and diversity, the collection was unparalleled. Some of the Burgess fossils had shells, many others did not. Some of the creatures were sighted, others blind.